Right now, the planet you are standing on is slowing down. A single day is 1.33 milliseconds longer than it was a century ago. For decades, we've managed this drift mechanically. Global timekeeping relies on Coordinated Universal Time, or UTC, which tracks Earth's exact rotation. To keep our highly precise atomic clocks aligned with the slowing planet, scientists have occasionally inserted leap seconds into the calendar. But deep inside Earth, swirling currents of molten metal in the core create their own complex rotational drag. Recently, those core dynamics caused a brief, sharp acceleration in Earth's spin. Because of this anomaly, global timekeepers are facing a scenario where they may have to subtract a second, a negative leap second, to keep clocks accurate. This chart displays Earth's rotational speed over 3.6 million years. Notice the severe drop on the far right. A 2026 University of Vienna and ETH Zürich study reveals the planet's rotation is decelerating faster today than at any point on this timeline. Human clocks are falling out of sync with the globe because Earth's internal core dynamics are drifting away from the speed of its crust. That change is being driven by the rapidly accelerating thaw of the polar ice caps. This cross-section of the globe illustrates a massive physical shift in weight. As trillions of tons of ice melt, that water doesn't stay locked in the Arctic or Antarctic. The newly freed volume flows away from the poles and settles in the oceans around the equator. This creates a problem with angular momentum. When planetary mass expands outward, the overall spin of the object decreases. Think of a figure skater extending their arms to slow down a tight spin. The wider the mass distribution, the slower the rotation. Human activity is now functioning as a geological force, redistributing enough surface mass to alter the rotational physics of the globe. Long before melting ice became a factor, an older, more persistent force has been bleeding energy from our rotation for billions of years: the Moon. This diagram shows the orbital mechanics of tidal friction. Earth completes a full spin in 24 hours, which is much faster than the 27.3 days it takes the Moon to complete an orbit. This rapid spin drags our ocean's tidal bulges slightly ahead of the Moon. In response, the Moon's gravity pulls backward on those bulges, creating a constant planet-wide friction. We can measure the exact cost of that friction using retroreflector arrays left on the lunar surface by Apollo astronauts. By bouncing lasers off these mirrors, observatories have confirmed that the energy transferred from Earth's slowing rotation is pushing the Moon 3.8 centimeters further away every single year. While lasers track today's drift, the long-term history of this slowdown is recorded in the growth rings of ancient marine life. Geologists can read these wavy sedimentary layers in 850 million-year-old stromatolite fossils like a biological clock. And those ancient layers prove that a full day back then lasted a mere 21 hours. Whether we look up at modern space technology or down at ancient sedimentary rock, the evidence points to a single, inescapable law of physics: the planet is winding down. A 2026 study from Purdue University uncovered a surprising biological consequence to this deceleration. In this split-screen data visualization, we can track how longer days influenced the oceans over millions of years. As Earth's rotation slowed, the extended periods of sunlight gave early photosynthetic bacteria more time to produce oxygen, which increased nutrient availability in global food webs. The friction decelerating the planet is a primary contributor to the rise of complex life, providing the extended daylight needed for massive oxygen production. The math of this deceleration stretches far out into the deep future. If we project the current rate forward, roughly 180 million years from now, a standard day will hit 25 hours. The final physical end state of this equation arrives in about 50 billion years. Earth will eventually achieve tidal locking with the Moon. Our rotation will match the lunar orbit perfectly, leaving one hemisphere in permanent daylight and the other facing an eternal night. For billions of years, the lengthening of the day was a purely cosmic transaction between a rock and its moon. Now, through melting ice and shifting oceans, human civilization has stepped into the equation, actively reshaping the physical timeline of the world we live on.